So we know that simultaneity is not absolute. Events that appear simultaneous to one person may or may not appear simultaneous to a second person. The question becomes then, since simultaneity deals with time, does time become relative as well? Let's try another thought experiment. We are in a spaceship moving with some constant velocity. Inside the spaceship, we have a mirror attached to one side and an observer that is stationary with respect to the spaceship that is some distance d from the mirror. We can say the observer is stationary because he is in the same reference frame as the spaceship. Event number 1 is a light beam sent from a light source towards the mirror. The beam is reflected back to a receiver, and this is known as event 2. To the observer inside the spaceship, the light appears to travel directly from the source to the mirror and back to the receiver. The question becomes, what is the time it takes for the light to travel from the light source and back to the receiver? Since it is light, we know that it is traveling at the velocity c. So we can use the total distance that the light travels, 2d, divided by the speed of light, to find the change in time. This equation tells us the time it takes for the light to leave the light source and return back to the receiver from the perspective of the observer inside the spaceship. We give this time a separate name, called proper time, to distinguish it from the time measured by an earthbound observer. Because then we can look at the same situation from the perspective of someone stationary on Earth observing the spaceship as it flies by. So this observer on Earth is observing the same ray of light that was moving from the light source to the mirror and back to the receiver that the observer on the spaceship saw. From this perspective, the ray of light will travel a different pathway with respect to the observer on Earth because the spaceship is moving with respect to the observer. So instead of traveling towards the mirror and straight back to the receiver, the light will move along the path with the spaceship. The light will appear to travel a diagonal distance. The light will hit the mirror and bounce back to the receiver. So relative to the stationary observer on Earth, the spaceship is moving to the right. The light then will travel in a diagonal distance shown. So the light is traveling a longer distance than it did according to the observer inside the spaceship. Since the spaceship is moving to the right, by the time the light beam moves from the source to the mirror, the spaceship has traveled a certain distance L. By the time it reflects back to the receiver, the spaceship has moved through space another distance L. Because the spaceship is moving at a constant velocity, the two L distances are the same. Since the speed of light is constant and the distance traveled by the light is more for the stationary observer, then that must mean that the time it takes for the light to travel a further distance at the same velocity must be more. So the time it takes for the light to travel inside the spaceship is less than the time it takes for the light to travel for the observer on Earth. The question then becomes, how much time does it take for the light to travel the entire distance as measured by the observer on Earth? We know that the speed of light is c, and this is a constant. Since this is also a velocity, we can say that the speed of light is equal to the total distance traveled by the light divided by the total time for the light to travel from the source to the mirror and back to the receiver. We measured the distance from the source to the mirror as seen from our Earth observer to be s. So the entire distance traveled by the light is 2s. This gives us a velocity of 2s divided by the change in time. Now it is important to note that this delta t is not the same as the delta t naught, or the proper time, that the person on the spaceship observes. This delta t is the time measured by the stationary observer on Earth. To find the actual length of s, we can draw a right triangle with a mirror and apply the Pythagorean theorem. S is the hypotenuse of our drawn triangle, d is the distance from the mirror to the light source, and L is the distance the spaceship travels. So s squared equals d squared plus L squared, or s is the radical of d squared plus L squared. So the speed of light is equal to 2 times the radical of d squared plus L squared divided by the change in time. This in itself is a fairly useful equation, but we want to relate this back to the velocity of the spaceship. The spaceship has traveled a total distance of 2L in a certain amount of time. This amount of time is the same amount that is measured by our stationary Earth observer. So the velocity of the spaceship can be expressed as 2L divided by the change in time. We can solve for L and find the velocity times the change in time over 2 as the distance that the spaceship travels. Now if you love algebra, you're going to love this next part. If you do not love algebra, I have faith that you're still going to love this next part. Because we're going to take our expression for L and plug it into our expression for the speed of light. We get this lovely equation that we can manipulate to our heart's content. Let's start with the expression squared in there. We can square the velocity and the change in time and the two. We have a few options from here, but the easiest thing to do is to square everything and get rid of that radical. The 4 in the denominator of our numerator seems a little problematic. In order to add the top two expressions together, we need a common denominator. 4 over 4 can adjust our d squared, which is even better because we have a 4 being multiplied to this whole thing, which means our denominators cancel out. Now we are left with c squared equal to 4d squared plus v squared times delta t squared divided by delta t squared. Remember, our original goal here was to find the difference in time. It is fairly simple to solve for the change in time. Really, all we need to do is switch the change in time in the denominator with a c squared, and we have a nice expression for the change in time squared. But we don't want to leave it just yet. Another way to write this is to say that the change in time squared is equal to 4d squared over c squared plus v squared delta t squared over c squared. You're probably wondering why in the world we want to do that. But remember that the proper time is 2 times d over c. You know what we can do with that? We can square it. We can square it and it looks exactly like that first expression in our equation. So now we have a relationship for the proper time, or the time it takes for the person on the spaceship to observe the light traveling in a straight line from the mirror to the receiver to the time that our stationary Earth observer is measuring. But we have an extra one in there on the right-hand side. That we can move over with our other change in time squared. So basically what we did here is we just solved for their proper time squared. And we get that equal to the change in time squared minus velocity squared times our change in time squared over c squared. Since we have our change in time squared in both of those expressions on the right, we can pull that out of both expressions. This looks pretty good, except we are really trying to find the time measured by our Earth observer. We can just divide the proper time by that whole 1 minus velocity squared over c squared. Of course, we have way too many squared terms here, so let's just take the square root of everything. This gives us the change in time for the stationary Earthbound observer as the time measured by our man in the spaceship, divided by the square root of 1 minus the velocity of the spaceship squared, divided by the speed of light squared. Kind of beautiful, don't you think? There are a couple important things to note about this equation. First, the elapsed time is not the same for the different observers moving relative to one another, and this time has to do with the inertial frame of reference for each observer that he finds himself in. The velocity of the moving object v squared is always going to be less than the speed of light. So the quantity in the denominator is always going to be less than 1. So delta t is always going to be greater than the proper time. This means that the time that has elapsed for the person inside the spaceship is going to be less than the time elapsed for the person standing on Earth. So the time for the moving observer always passes more slowly than the time passing for a stationary observer.